Hi, I'm Kevin Flood. I'm the Vice President of Engineering here at Analytical Graphics, and I'm going to spend a few moments talking about what digital mission engineering is and why it's important for the missions that we're trying to address today. So let me start with some preliminaries, talking just about the definition of digital mission engineering. Like anything, a term can have a lot of different meanings, but from our perspective, it incorporates four distinct elements. First of all, digital mission engineering is the incorporation of digital modeling, simulation, and analysis. So similar techniques to what we use for engineering simulation or mathematical analysis. But in digital mission engineering, a unique component is that we bring in the operational environment. So we spend a lot of time talking about engineered systems and designing for functionality. What we want to do with digital mission engineering is bring those entities into the physics-based environment in which they're going to operate. And then when we do that, the third component of digital mission engineering is being able to evaluate the operational effectiveness, the mission outcomes, when those physical systems are used, and they're used in accordance to the CONOPS and the rules with which they're built. And the final component of digital mission engineering is that these techniques are applied all throughout the engineering lifecycle and into operations. So that's the foundational definition that we use when we talk about digital mission engineering, and that'll be applied throughout our workshop today. What I'd like to talk about now is why DME is so important at this present moment. To do so, I'd like to first sort of set the stage for the phenomena that we're seeing throughout our aerospace and defense and larger marketplace in general, where systems of systems are coming together to address really critical missions in our marketplace today. So what this graph shows is the competing elements of two very critical criteria. First of all, on the left axis is complexity, and complexity applies to multiple factors. It applies to the types of missions that we're trying to address, and that can be in the defense world, it can be in the scientific exploration world, it can be in infrastructure for 5G systems and smart cities, any variety of applications where mission is an applicable definition. And where we're addressing those missions, the systems that are being used to execute the missions are much more complicated as well. So the missions are more complicated and the systems are more complicated. And then when we look at the engineering processes that are used to develop the systems, they are executed by distributed teams using very sophisticated tools in multiple disciplines that need to come together in, again, a complex way. So the level of complexity is extremely high. At the same time, the competing element is the tolerance for the delivery time, which is shown on the bottom axis. So whether we're trying to respond to a threat that's imminent and rapidly arising on the defense front, whether we're trying to execute a search and rescue or a humanitarian aid mission, or whether we're trying to be the first to market with smart city technologies or 5G technology, the timeline that we're willing to put up with is extremely low. So the fact that we have these two opposing factors competing with each other in an extreme way that we see today really mandates that we address a fundamental revolutionary change in the way that we do business. We can't tolerate incremental changes in the execution of the development of our systems any longer. And this is where digital mission engineering comes into play. So the way we'd like to talk about how digital mission engineering can improve this situation is to look at it in the lifecycle context, which we show here in this elliptical lifecycle chart going clockwise from the upper right-hand corner in concept development all the way through operations and sustainment. So for the kinds of operations that we're talking about, the thing to consider here is that first and foremost, the mission has to be the center of our attention, and it has to be linked to every decision of consequence in this process. So we'll illustrate that by this picture in the center of the process. But around this process exist multiple forms of information. And if we look at how that information is used today, one of the things that we notice is that there's a fundamental disconnect. So if we focus for a moment in the concept development phase, we see a situation like this, where we have a variety of models that describe the mission and the systems of systems at a high level. And we're familiar with many of these models. In the defense world, these are DODAF models. They're descriptive models of various types, and they're documents. And outside of that, exist a variety of physics-based or calculation-based analytics that help us evaluate and make decisions about all the things that we're trying to address with regard to the mission and the systems that we're constructing. And the thing that we notice is that there is no direct connectivity between those items. The models and the physics-based representations are disconnected, and furthermore, the physics-based representations themselves are disconnected from each other. The result of this is that we have human professionals making all of that connective tissue, which is very effective in that we can mine the intelligence of those individuals, which is a critical component of this, but it also becomes very error-prone when these systems get to be very complicated, like the ones that we're talking about right now. And as we evaluate how this perpetuates throughout the entire life cycle, we see that the situation gets worse as we move from phase to phase in the life cycle. So not only are these different model types disconnected from each other, they're disconnected from phase to phase, which results in a lot of reinvention and the repetition of work across many phases, the disagreement and misalignment in models that are used to inform decision making, and the disconnection between our requirements processes and our engineering processes in general. So what this results in is an extreme extension of the time it takes for us to bring our systems into operation and to make our operational decisions. So the promise of DME then is really to make that connection between the mission and these processes more streamlined. And it really lies on the back of some other fundamental concepts that we're trying to execute in our industry today. And that is the notion of a digital thread. So first and foremost, we need to integrate a mission model that becomes a persistent thread and an authoritative source of truth throughout the entire engineering process. And within that mission model are all of the other models of significance, from the system of systems all the way down to the component model. Now, on top of this, what DME brings to the table are the following two components. First of all, DME allows us to pull forward levels of fidelity and different models. And that isn't to say that we need to complete, for example, the detailed component design in the concept development phase. However, none of these systems or missions get executed in isolation. So there are very many models that are already in operation which are going to integrate with new models and new missions and new systems that we're going to engineer. And digital mission engineering allows us to bring those existing models and utilize them in a very important way all the way up in the concept development phase. And then we wrap this entire process with a multi-domain physics-based environment and connect all the models to that environment so that every decision that we make, whether it's an engineering decision about the engineered systems, the architecture, or whether these are operational decisions, can be connected back to that mission. And likewise, at the low-level engineering design process, we can evaluate each of the decisions that we're making in our detailed design trade-offs back to the mission and continuously validate that the mission requirements are being met. So at a high level, this is the promise of digital mission engineering. And in our assessment, looking at case studies and doing surveys, looking at leaders in the technology and doing some of our own prototyping and experimentation about the outcomes that can be achieved using the techniques that we're talking about, we've observed the opportunity to increase between 2.5-fold and 6-fold with regard to compressing this entire life cycle, depending on the complexity of the situation. So definitely an opportunity to bring forward that revolutionary kind of change and not just the incremental change. So that is why digital mission engineering is really important to us today. And before I leave here, one of the things I'd like to talk about is what we can do next. The concepts that I've talked about and the technologies that are in place right now allow us to do much of what we've just described. However, it requires us to implement some fundamental changes in our engineering and acquisition processes and some of our organizational operations, which are big, heavy lifts and hard to do. So in our interactions with our customers and some of the thought leaders in the industry, there have been 4 specific areas that we think we can apply right now that can make a fundamental change and move the process along. So I'd like to quickly go through each of those 4 as specific steps that we can take right now to apply these mature technologies in today's world. And let me go through each of these one at a time. So the first one is the idea of integrating the design reference mission model into the engineering process. So the idea of a design reference mission is fairly common throughout our industry. It is a model that defines how we're going to execute the mission and what the operational outcomes are. But in general, that hasn't been intimately connected to the engineering process. So as we just illustrated in the prior diagrams, connecting this directly into the engineering process can yield significant acceleration of the overall engineering life cycle. And that's largely what you're going to see in the demonstrations this afternoon. And let me highlight some of those specifically. So if we go back to our digital thread model, we'll see in this afternoon's demonstration that we'll use a combination of descriptive models and physical models to describe the mission and the system of systems architecture. We'll be using Cameo System Modeler from Dassault Systems NoMagic and AGI's Systems Toolkit to accomplish that. Additionally, we'll be using a variety of multi-physics tools from ANSYS for some of the more detailed design. And then we'll use AGI's Systems Toolkit to bring that multi-domain physics environment into the picture, and then using Phoenix Integration's Model Center to enable those connections, and that can be applied throughout the entire life cycle. So this will illustrate what can be done today using technologies that are fairly mature and being used and have been used for a number of years for this specific purpose. And the important component here is that we can use the descriptive models and the physical models together to capture that design reference mission and make sure that we validate consistency with it all throughout the entire life cycle. The second component flows directly from the first example, and that is to design with executable architectures in mind. Now, the topic of executable architectures is discussed broadly in the literature and in our community and has a variety of definitions, but what we're talking about here is ensuring that we integrate the architectural construction, the hardware design, the software design, and then the concept of operations and the tactics that we're going to apply for executing our missions into the design process as well. So it's really about integrating the behavioral models with the physical models and the environmental models in the process as well. The technologies to support this are less mature than the ones we're illustrating today, but are definitely online, and we'll be doing some more communications about that in the coming weeks. But this is an important component so that we can trade off the way we use our systems alongside of how we build our systems and architect them. A third and very important component is ensuring that we include test and evaluation at every phase in the life cycle. And test and evaluation is an important component to consider in the overall engineering process because of its criticality. So first of all, no system gets delivered unless it passes the test and evaluation process. So that's a fundamental gate. But over and above that, it's such a heavy contribution to the overall program timeline. What I'm showing here are some results from a RAND Corporation study that's now a number of years old, but the numbers still line up with what we're experiencing today. This study looked at a variety of aircraft programs and guided weapon programs that were executed over a span of about 30 years. And what the RAND Corporation found is that over that 30-year period, in spite of advances in test and evaluation technologies and processes, the timelines and the respective costs of test and evaluation did not go down. And that had to do with the complexity of the systems that were being tested going up. Again, that speaks to the fact that we need some step change improvement in the way that we execute these programs in order to bring about fundamental change. But an important component that was brought out here is the scale of the contribution of the test and evaluation effort. It consumed between 15 and 20% of the total delivery cost for the program, but probably more importantly, it consumed 50 to 75% of the time of the program, which amounted to about 50 months on average. So the way I was thinking about this is if I could shrink every other activity in the critical timeline down to zero, but the test and evaluation process, it would still take us over 4 years to deliver the systems. So what we're trying to accomplish with digital mission engineering is to compress that component even further. And a couple of ways to think about that will be addressed peripherally in today's demonstration are to look at the ways that test and evaluation are, number one, informed by other activities, or also inform and contribute to other activities in the life cycle. So by taking that into account in the early phases of the program and getting a well-established design reference mission, we can accelerate the timeline for the test and evaluation process. But more importantly, we need to recognize that test and evaluation is not a discrete event. It doesn't just happen in one phase of the life cycle. It's distributed all throughout the program and in various other activities. So if you look at where test and evaluation activities actually occur, they occur all throughout the life cycle. And using digital mission engineering techniques allows us to accomplish that with great outcomes. So whether that is validating mission and architecture concepts in the early phases, or that is early and more effective integration of software under development or hardware components under development through the integration in the software integration labs and the hardware integration labs, tying those activities back to the design reference mission through DME techniques, or all the way up into the continuous improvement and the sustainment increment evaluation in the later phases of the life cycle. The test and evaluation process, being an ongoing and integrated component, brings dramatic reduction into the overall program life cycle. And one other outcome that's critically important here too is that we think about test and evaluation being applied primarily to the delivered system, the hardware system and its associated software. But through this process, another thing that's happening is that we are validating the digital twin representations of these systems all throughout the life cycle, which means that we come out of the engineering process with validated digital twins, which allows us to achieve our fourth component, which is to accelerate operation through the use and application of those digital twins. You know, this is a technique that has not been utilized a lot, certainly in aerospace and defense, at least on a broad scale. But I know we here at AGI are familiar with this concept, and for us it hasn't been a new concept. I'm reminded of a user conference presentation from 2008 when the Marine Corps Combat Development Center, MCCITC, used these same types of techniques to execute a analysis of alternatives for small tactical UAV systems. And they did it with fantastic outcomes. And they cared very much about where these systems were deployed. So they cared a lot about the environmental modeling, and they cared about all of the integrated mission systems working together, the communication subsystems, the radar systems, the imagery collection, the performance of the aircraft. So they were able to demonstrate in this small isolated study an incredible design and analysis of alternatives using these techniques. And in the following year, the operational teams who were being deployed in Afghanistan looked at that study and they said, we need this same capability to execute our missions and do our mission planning. So in a span of 6 weeks, from the first recognition of that need to having troops on the ground in Afghanistan with this capability deployed in a mission planning form factor, only took 6 weeks. So there was good validation from more than 10 years ago that these techniques can be applied in this way and can accelerate design life cycles. Now clearly the overall scope of that program was more limited, which allowed them to do this very controlled experiment to apply these techniques. But at a fundamental level, there's no reason why we can't apply these techniques in a broader scale and achieve similar outcomes. In talking about the operational outcomes, one of the components of the terminology that we're starting to introduce is this notion of digital mission operations. And the reason we're doing that is that the operational teams are fundamentally different audience, and they don't think of making engineering decisions the way we might do it on the engineering side. But nonetheless, the same technology stacks that apply to the engineering process and engineering decision making apply to the operational decision making, as we saw in the Marine Corps example. The only difference being in the engineering life cycle, we're trying to make decisions about hardware and systems that don't yet exist and making sure that they apply to the mission that we want to conduct. And on the operations side, we're using those validated digital twins to inform decisions that we're making about the operations that we are already conducting. So this is a new addition and augmentation to the notion of digital mission engineering, but again, it's the same fundamental technology stack that applies. So in conclusion, the notion of digital mission engineering and the augmentation with its application for operations is really about linking engineering with the mission, whether that is making sure that the mission and its outcomes are tied into the engineering process and the decision making, or whether it's using those engineering outcomes either in the form of the delivered system or the digital twins to execute the mission. There are a lot of factors that are going to have to be addressed in order to realize the vision of shrinking our overall life cycle. But the digital mission engineering is definitely one important component to integrate in order to bring about that success. And the good news is that the technologies are available right now. They're mature and have been demonstrated to solve these same kind of problems. And we have at least 4 areas where we know right now we can start addressing and bring about some of these important impacts. So I hope this provides a good background on digital mission engineering and why it matters today. Thanks for watching. And if you'd like any more information, please come to agi.com or drop us an email at info@agi.com.